So the synthesis and reactions of conjugated systems is going to be here in this presentation. Again, it's not huge, kind of short. So first of all, the synthesis. Again, remember what synthesis is for conjugated system, just like it's an alkene, right? So if it's an alkene, then you will do elimination reactions. The only thing over here you need to kind of watch out is that most of the eliminations are going to be E2, okay, not E1. E1 means through carbocations. So we don't do those kind of eliminations. Most of the eliminations will be E2, which means that you will be using a base, okay, in there, a strong base. Usually a bulky base will ensure that you have elimination. You can use ethoxide, methoxides also, that's all fine, okay, but the main thing is that you have to use a base and you have to use an alkyl halide, okay, for making a conjugated systems. Now you will need 2 halides in there because you need to do 2 eliminations. What I've shown you here is the halides, whether they are 1, 3 or 2, 3. Okay, even if they're next to each other or not next to each other, they will still give a conjugated system. Okay, so in this case, you don't have much choice anyway, right? Because we have only 4 carbons. But even if you didn't have 4 carbons, and you had like 5 carbons in this one, you would still get a conjugated system because conjugated system is more stable. All right, so that is the goal generally for any kind of a compound, is to be more stable. So here you can take any of these halides and do an elimination. Again, heat is going to promote eliminations, all right, especially the E2 kind. Even E1 they promote, but anyhow, and then you get a conjugated system here, okay? So if you wanted to make a conjugated system from an alkane, how would you start? From an alkane, the first thing you would do is halogenation using light. So this is more like a free radical reaction. Then you do one elimination on this one. So once you have a double bond, now what you can do is another free radical reaction with NBS. NBS is very specific for giving a bromine in allylic position. So once you have the bromine in the allylic position, you do another elimination and you get the conjugated system. Now, when you're doing the elimination, you have to remember that, you know, the elimination, you can get a hydrogen from here also, but that hydrogen is not going to be used because you will get then accumulated system, which is not a happy system, okay, or a stable system. So you will make a conjugated alkene, okay? So this is how the elimination works. Now, you cannot use alcohols for these kinds. So for example, if you did have cyclohexanol to start with, sure, for the cyclohexanol, you can do the dehydration. Once you do the dehydration, and let me write that down, okay, so you can see how that's working. But if you had like cyclohexanol to begin with, sure, you can do dehydration on that, okay, and that will give you something like this. If you have something like this, that puts you right here. Then you can go ahead and do the NBS and then do the second elimination, okay? But you cannot add another alcohol, or you cannot take a diol and then do 2 eliminations to get a diene. That's not how it works, okay? So be careful with that. All right, so that's it. That was a synthesis of dienes. There's nothing really much fancy going on. So now let's look at the reaction on conjugated dienes. All right, and this is not just dienes. It could be on any kind of a conjugated system. Okay, so first of all the reactions are going to be still addition reactions. Okay, so there's not like I'm changing any of that. Just like an alkene does an addition reaction, the conjugated system will also do an addition reaction. Okay, so that electrophilic addition is going to be on the double bond. Remember, the double bond is the electron rich, so that's the nucleophile. Okay, so generally when you take an alkene and you want to do addition reaction on it, so for example, you want to take this diene and you want to do, you know, add HBr to this. So once you do that, you should end up getting a product like this, okay, where you have the 1,2 addition here and the 1,2 addition here. Now remember, this is going to be a Markovnikov product, right? Hydrogen goes to the carbon with more hydrogen. So it's supposed to be a Markovnikov, so that's how I've written this. But not generally, but when you do the reaction on this diene, you actually never get this product, okay, at all. So if you don't get this product, what are you getting? these are the products you get. Okay, and I've numbered all these things because it's really important for you to see where the addition is taking place. Okay, and I want you to note, first of all, you're not adding two HBRs. Here you're actually adding two HBRs, right? Because you had two bromines in the product. So technically it's this, right? So you have one HBr here and one HBr here. Now, if you look at this products over here, in these products, you only have one HBr because that one double bond did not react, or it's still there, we should say, right? And then in the other product, you still have the HBr, but now the location of the double bond has moved. Okay, so the way we classify these products is how the addition has occurred. So in the first case, you can see that the addition is a 1,2 addition because you just added the HBr just like you would add on a double bond, on an alkene, a 1,2 addition. Okay, that's how it's supposed to be. And that's how it is in the first product. The second product, however, is a mystery because now what has happened is you've got the hydrogen in the first carbon, just like here, but the bromine now is on the fourth carbon. Instead of being on the second carbon, bromine is on the fourth one. So which means this is going to be a 1,4 addition. So two things have happened here. First of all, you've added only 1 mole of HBr. Okay, that's one of the things. The second thing is you're getting two products, right? 1,2 addition and a 1,4 addition. So then there are questions, right? Of course there are questions like, are they equal in proportion? And why are we getting these? Why is it only 1 mole of HBr? All of those kind of questions then start popping up. Okay, and so it needs an explanation as to what's going on over here with this kind of an addition. You can do this with HCl also and get the same products. Okay, so what is the explanation for this? All right, so you have to write the mechanism. That's what we do in organic chemistry, is we try to explain writing mechanism. So the first thing we do is, of course, start with the HBr, right, and the double bonds. The double bond picks up a proton over here and you get your traditional carbocation that we usually get in Markovnikov additions also, or any addition reaction. So you have the hydrogen attached to the carbon with more hydrogen, and then you generate the carbocation. Now what happens is, because there is another double bond, you end up having resonance. Okay, so the red arrow shows you the resonance going on. And so once you have resonance, now the carbocation has shifted from this location, from the second carbon to the fourth carbon. Okay, this kind of resonance is not resonance itself. The cation, this is an allylic cation. Okay, and this allylic cation is actually very stable, all right, because of resonance. So you might think, oh, but this is a primary carbocation, but no, there is resonance, and resonance leads to more stability. Okay, so even though you have a primary carbocation, it doesn't really matter. Okay, resonance is more stable. Resonance actually in any kind of cation is even more stable than a tertiary carbocation. Okay, so resonance is a huge deal in organic chemistry, or in any chemistry for that matter. But anyhow, so here you have then two resonance structures because of the double bond. Now, depending on the number of double bonds, you can have more, but I'm limiting here to what we were studying before. So now this carbocation will add on the bromide, okay, and give you the 1,2 addition, and the carbocation, which has moved to the other location, to the fourth carbon because of resonance, will give you then the 1,4 addition. Okay, so that is the explanation of why you have these two products. Okay, so this is because of resonance, and that's the big deal for dienes. So now let's talk a little bit about the product. So here's the mechanism again. Okay, so here's the resonance going on, and you have the 1,2 product and the 1,4 product. Now the 1,4,2 product is actually called the kinetic product. The 1,4 product is called thermodynamic product. So I've given you some properties over here. Okay, so the major product at -80 degrees Celsius, which is really very, very cold, this is the major product. The 1,2 product is the kinetic product. That's the major product. At a higher temperature, 40 degrees, which is really not that hot, so but still on a hot, you know, it's room temperature for some locations, the thermodynamic product is the major product. Okay, so which means that you don't even have consistency of major products, okay? That you will always have a 1,2 as your major product or the 1,4 as your major. It's not that, it is temperature dependent, okay? So that's the thing. So now what do we explain this with, okay? How do we explain this? So the 1,2 addition product that we are forming at negative 80 degrees Celsius, a very low temperature, is called kinetic because this is happening really fast, okay? Which means the 1,2 addition is a really fast addition. The thermodynamic product, on the other hand, is a slow product. Why is it slow? Because it needs to go into resonance, okay? So only you can form this product after resonance has been completed, okay? And so after resonance, then you have this. To do resonance, you need a little bit energy. So the thermodynamic product, then it forms only at a higher temperature because you need a little bit more energy, okay? Now, which is the more stable product? The thermodynamic product is the more stable product. Why? Because it's undergone resonance, okay? So because of resonance, this is going to be the more stable product. This one forms immediately. Kinetic is immediate. Thermodynamic is after a little while. This is love at first sight. This is love after a while, you know, when you have friendship, that kind of a thing, okay, going on here. So that's the explanation of the major and the minor product. So when you get reactions like this, you really have to note the temperature, okay? So if it is at a higher temperature, and higher doesn't really mean 100 degrees Celsius. Higher can even mean, like as it says here, 40 degrees or 50 degrees Celsius, okay? And look at the percentage of product that's occurred. Now, one of the things that can happen, okay, with these two kind of products is that if you decided that you wanted to make a 1,2 product and you have a conjugated system, okay, and you're like, okay, I'm going to make this product, and then tomorrow I'm going to come and do, you know, more reactions on this. And you make the product and you leave it in your drawer or you leave it outside on your bench. Well, tomorrow you will have the thermodynamic product. Okay, so you will not have the 1,2 product anymore. What that means is that the product itself will then undergo resonance to form the thermodynamic product, even if you're not doing the reaction, okay? Because this product is so stable that it will undergo resonance and give you the thermodynamic product, okay? So if you wanted to work with the kinetic product, either you work right away with the kinetic product, okay? Or you keep it at a really low temperature until you're ready to use it, okay? Because given room temperature, it's going to change to the thermodynamic product. Cyclic dienes also will give you the same thing, okay? So here is an example, and you can use bromine here. So I used HBr before because it's easy for us to see where the hydrogen is going, but bromine, same thing, you know, it will give you the same thing. So which means this is a 1,2, this is the 1,4. Now, I will advise you always when you're doing these kind of reactions is to number your carbons, okay? So here is the 1, 2, 3, 4. So write it out, and that way you know where you're adding your bromines, 1 and 4, and this is 1 and 2 then, okay? So there is absolutely no shame in writing numbers. So go ahead and write the numbers and clarify for yourself where you're adding everything, okay? So here, if you're taking the same cyclic compounding and adding HBr, you might think that, oh, I'm going to get these two products because here I'm doing the 1,2 addition and here I'm doing the 1,4 addition. But it turns out that in this case, you're actually doing the same reaction. Okay, so both of the products are exactly the same because once you start numbering them, and when you start naming them, I should say, then you will still get the same thing, which is 3-bromocyclohexene. Okay, so remember 1, 2, 3, and then 1, 2, 3. So the final product is the same. So you have to be careful. Okay, so bromine, you get two products, but cyclohexadiene with HBr gives you only one product. Now, you know, I mean, depending on what you want, you just make what you want. I'm just saying that be careful that just because you can write two things does not mean they're different. Okay, so always number your carbons, and if you're ever in doubt, name the structures. Okay, name them and see if you're coming up with different names. Let's look at what happens when you have substitutions on the dienes. So for example, if you look at the first alkene here, it has a methyl group. The second one does not have that, so this is more substituted. So there are few possibilities here, right? So if the first double bond attacks the hydrogen, this is the carbocation you form. The second one attacks over here. There are two possibilities of forming a carbocation on the left carbon and the right one. Now, neither of these form. Okay, why so? Because this carbocation is a lot more stable than either of these two. Okay, the last one over here, this one will not even form because this is, it cannot even undergo resonance. So this is definitely not going to form. But this one also is not going to form because this carbocation is much more stable. Okay, so when you have substitution, you always have to start with the carbocation that's going to be more stable. Now you will still get resonance, you will still get the 1,2 and the 1,4 products. Okay, that is still there. The kinetic thermodynamic is all there. It's just about where do you start your reaction. That's the main thing. Okay, be careful with that. And I think that's all there is to this. So make sure you go through the synthesis and the reactions. Again, it's a, very straightforward kind of short synthesis and reactions.